you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and I have another Algebra 2 tutorial for you today. We're going to be talking about extending our real number system. These are the set of numbers that you've been using ever since you've started school and you've started to count. And today we're going to find out that there is another set of numbers that, in addition to these, that you haven't heard about yet. Now, these numbers were motivated by solving, say, a quadratic equation like we have here. So if you remember, to solve a quadratic equation, a simple one like this, we could subtract 16 from both sides and solve using square roots. So to solve using square roots, we're going to take the positive and negative square root of both sides of the equation. And we get x here. And now this would have been, up until now, undefined or no solution, because we can't take the square root of a negative number. So in the late 1500s, a mathematician defined a new number called the imaginary unit, and the properties of this imaginary unit is that I squared equals -1, or you could also view it as I equals the square root of -1. So now if we include this new number as part of our number system, now when we solve this, we get plus or minus the square root of -16, and we can simplify our radical here by splitting that up into the square root of 1 times the square root of 16, which would then be I times 4, or we will normally write this as 4I. So now we can solve all quadratic equations and polynomial equations that here to now were unsolvable. The invention of this was controversial at first. The real world meaning of this was not appreciated, but throughout the years, the invention of this has allowed for, or has been crucial in lots of engineering and physics applications. And for example, in modeling complex electronic circuitry, if we could not solve equations that involve taking the square root of negative numbers, we would not be able to use the math, and we might not have today's cell phones. So let's explore these a little further. So again, one of the operations that we will be doing will be to simplify radicals. Now, if you just remember from earlier in algebra, to simplify a radical, especially if it's not a perfect square, we will be looking to divide out the biggest perfect squares into the radical. In addition to that, now that we have the negative signs, anytime we have a negative under the radical, it will become an imaginary number. So 49 is a perfect square, so we could split this into square root of 49 times square root of -1, which would be 7i. So again, we'll break out the -1, which will become the I. Now, 49 divides into 98, so this splits up into the square root of 49, and this times the square root of 2. So now we've got 7 radical 2 times I. Now, just a notation, because it's not always clear how far this radical sign expands out, we will always put the I in front of the radical notation like that. And here 243 is divisible by 81, so we get the square root of 81 times the square root of 3 times the square root of -1, which is 9. Now I'll put the I here, square root of 3. So You may need to go back if you haven't remembered how to simplify or reduce radicals. Again, we are taking these numbers, finding the biggest one that divides into our number, breaking that out. And the new skill here is if we have a negative under the radical, instead of saying no real solution, if we are including these imaginary numbers as part of our solution, we will tack on an I. I, as we raise it to exponents, has some interesting properties. Ultimately, we're going to want to be able to figure out what's the value of I to the 49th power. But let's look at here. So we're going to start with I. If I multiply it times itself, I get I squared, which has been defined to be -1. If I look at I cubed, that's I squared times I, because remember we add our exponents. But I squared was just defined to be -1, so we have -1 times I, and we get -I. If I take I to the 4th, that'll be the previous number, I cubed times I, which gives us -I from the previous answer for I cubed times I, which is -I squared, but I squared is -1, so we get +1. And when I get to I fifth, I would be I to the 4th times I, which in this we just decided here was 1. So 1I or I. And this pattern keeps repeating. So every 4 powers of I, we cycle through I, -1, -I, +1, and it keeps cycling. To solve problems like this, which will show up sometimes on standardized tests, the skill will be to factor out powers of I squared. So let's make this be an even exponent. So let's break this up into I times to the 48th power times I. Remember, on exponent properties, we are adding the exponents. And now let's break this up into powers of I squared. Now remember, when we use our power to a power rules, that's a 4 there. Remember, when we raise a power to a power, we are multiplying. So 2 times 24 gives us the 48. Now we know from over here, I squared is -1. Now when we multiply -1 times itself 24 times, if we have an even power here, this value will be +1. If we have an odd power, it would be -1. So here this is even, so we have +1 times I, or I. So when we simplify I to the 49th, it equals I. So again, the whole trick is to factor out powers of I squared using exponent properties to find out what remains. Now, after the invention of this imaginary unit, over the next couple hundred years, mathematicians formalized these imaginary numbers and created an entire number system called complex numbers. Each complex number is made up of 2 parts, a real part and an imaginary part. A and B will be real numbers, coefficients here. So with the inclusion, or this the definition of complex numbers, every number that we have is a complex number, because our existing real numbers, say 2, could be written, so 2 could be written as 2 plus 0i. So while this is a real number, it is also a complex number. Purely imaginary numbers, like we looked at a minute ago, 4i, could be written as a complex number as 0 plus 4i. So this definition of a complex number can encompass all the possible numbers, and we will be using this number system now as we solve quadratics. Now, when mathematicians create a number system, they have to define an entire set of operations, things like adding, subtracting, multiplying, dividing, taking absolute value. So we need to know how to perform these operations on complex numbers. And it's a lot like when we talk about adding and subtracting, it's going to be a lot like simplifying algebraic expressions, our key skill we're going to be using is combining the like terms, meaning we will be combining the real parts together by adding them and combining the imaginary. So if we combine the real parts here, we've got 3 plus 5 is 8, and 2i minus 3i would be negative 1i. Here we can distribute this minus to the entire complex number and then combine our like terms. So 3 and negative 5 would be negative 2, and 2i plus 3i would be 5i. When we do multiplication, we will be using FOIL or the distributive property. So we will be taking 3 times 5 is 15. Now 3 times negative 3i would be negative 9i. 2i times 5 would be 10i. And 2i times negative 3i is negative 6i squared. Now we need to do two things to simplify this. We can combine these like terms, but one of the fundamental definitions that you need to remember for imaginary numbers is that I squared equals negative 1. So we can simplify this I squared here by replacing it with its value, which is negative 1. So now this part is a real part. So we have 6, and now we have negative 6 times negative 1 is positive 6. So 15 plus 6 is 21. And negative 9i plus 10i is 1i, so plus I. So when we are multiplying complex numbers, we will be using distributive property or FOIL and combining like terms, and then we will never leave an I squared in our final answer. Anytime we see I squared, we will be replacing it with a negative 1 and simplifying. Now there are special pairs of complex numbers where the real and imaginary parts are the same, but in one case we have the real and imaginary part added together, and the second we have the real and the imaginary part subtracted. These are called conjugates. And conjugates have a interesting property when you multiply them. So let's pick a pair of conjugates. Let's say 3 plus 4i. And let's multiply it times its conjugate, which would be 3 minus 4i. And let's see what happens. So 3 times 3 would be 9. 3 times this would be negative 12i. 4i times 3 would be positive 12i. And 4i times negative 4i would be negative 16i squared. And let's simplify it. We have positive and negative the same thing, so those will add up to be 0. And we're going to replace this I squared with negative 1. So this becomes positive 16, and 9 plus 16 is 25. When you multiply conjugates, you will always get a real number. So if we just do it in math and algebra in symbolic terms, we have here, we could have also used that over here. We have a difference of two squares. I'm sorry, yes, the fact that we have a factored pattern of a difference of two squares. So when we FOIL this out, we're going to get the first thing squared, the a squared, minus the second thing squared. And this is going to be, when we simplify it using our exponent properties, b squared times I squared. And remember, this is negative 1. So we end up with a squared plus b squared. So when you multiply conjugates, several things happen. One is you get a real number. And secondly, you can compute it by taking the coefficients of the real part and the imaginary part, squaring them and adding them together. Now we're going to use this to simplify complex number fractions or division. So we're not doing division in the sense of the way we would do long division with real numbers, but we are going to simplify them so that the denominator of the division or the fraction is a real number. So this will be similar to the way we rationalize radicals. So I can't leave this with a I in the denominator. And we just learned on conjugates that if I multiply the bottom by its conjugate, we will turn the denominator into a real number. Now, when we're dealing with fractions, if I multiply the denominator by something, I have to multiply the numerator by the exact same number. So we're multiplying by 1. We're not changing the value of our complex number. On the bottom, from what we just saw, we're going to get 5 squared plus 3 squared. And on the top, we're going to have to distribute this out, FOIL it out, so we're going to get 15. And 3 times 3i will be 9i. And 2i times 5i will be 10i. And 2i times 3i will be plus 6i squared. So on the top, this becomes negative 6, and plus 15 becomes 9, plus 19i. And on the bottom, we've got 25 plus 9, we get 34. And now we want to write that as a complex number, meaning a real part and an imaginary part. So we are going to split this into 2 parts, 2 fractions. So the 34 divides into both parts. So this is the result we got when we divided this complex number by that complex number. But we did it by multiplying top and bottom by conjugates. Finally, absolute value measures the distance of a number from the origin. And we didn't talk about graphing complex numbers. You can look that up. They are graphed on something called a complex plane, but it again is the distance. So we can use the distance formula or the Pythagorean theorem to figure out that distance. So here's our formula for absolute value of a complex number. So let's just practice that. So here we've got square root. Now my a is the real part. So I get 3 squared, which is 9, plus 16. So we have the square root of 25, which is 5. So the absolute value of that complex number is 5. Here, 3 squared is 9. Negative 4 squared would be negative 4 times negative 4 is also plus 16. So again, we get square root of 25, which is 5. Here, the imaginary part is 0, so I get the square root of negative 3 squared, which is 9, plus 0, which is the square root of 9, which is 3. And lastly here, I'm going to get the square root of 0 plus 9, or it's also going to be 3. So if it's a real number, this works out so that the absolute value works the same way it always has with real numbers. If it's an imaginary number, we will just get rid of the imaginary number and change it to a positive. And lastly, when we square root complex numbers that have both a real and an imaginary part, we will get a real number. Now again, the reason we are talking about complex numbers now is we've been talking about in the last couple of lessons solving quadratic equations. And up until now, if we were taking the square root of a negative number, we would stop and say no solution. Now, if we include the complex number system, we can solve all of these. So let's look at some sample problems here. So we did one like this in the lesson opener. So we can solve using square roots. So we get the x squared by itself. We square root both sides, and remember when we take the square root of both sides of the equation, we want to take both the positive and the negative square root. And then in the opening slides, we talked about how to simplify this. So we get square root of negative 1, which is going to be I, and 48 is divided by the perfect square 16. So we've got the square root of 16 and the square root of 3, and this is going to become plus or minus, this will be 4i square root of 3, so 4i radical 3. This one's the similar, except we don't have just x squared, but we do have a squared item, so we want to get that by itself. So I'm adding the subtracting the 31 to get it to the other side. Now I can square root both sides of the equation, remembering to take both the positive and the negative square root. Now when we square root something that's squared, it undoes the square. Now 24 is divisible by the perfect square 4, so it's 4 times 6. So this is going to be square root of -1, square root of 4, square root of 6. So we've got x minus 3 equals plus or minus, this is going to be 2I radical 6. And now we need to get the x by itself, so we're going to add 3. This is a real part, this is a complex part, so to make it look like the standard form of a complex number, we will be putting it into the standard form for a complex number. Now this again represents two numbers, and it's an important part here with complex numbers. This represents 3 plus 2I radical 6 and 3 minus 2I radical 6. When we're dealing with complex solutions to quadratic equations, if you have a complex solution, it will always come in conjugate pairs. So this is 0 plus 4I radical 3 and 0 minus. It's a pair of complex conjugates. This is a pair of complex conjugates, so they will always come in those pairs. Now our last problem here, we will use what we just learned in the last lesson. We will solve it using completing the square. There's no coefficient here, so we don't have to divide. So remember, we want to get the x terms on one side of the equation and the numerical part on the other. And remember, we are going to be adding a number to both sides. We want to turn this into a perfect square. Remember, the number that goes here is going to be half of this number, half of b divided by 2. And then we're going to square that. So we're going to take -6 squared, which is 36, to both sides. This factors into x minus 6 squared. And on this side we have -8. Just now we look just like this problem here. We're going to square root both sides. And we will simplify this. 8 simplifies to be 2 radical 2, and with the negative, so we get 2I radical 2 plus or minus, and that equals x minus 6. And we add the 6, and again we get our complex conjugates. So that wraps us up for complex numbers. One interesting thing, an application of complex numbers that you might want to research is called fractal art. You might have learned about fractals in geometry. Fractals have a power, if you zoom into this picture anywhere, it's the same pattern repeating in an infinite manner. Modern day movies, some of the computer generated backgrounds in some movies have been used using the mathematics of fractal and fractal art. So enjoy complex numbers. They're not as difficult as the name would say. They're not so complex, and good luck and see you around.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you